little bit about me. I'm not going to spend too long. I've been working with Oracle about half my life now. I've worked on predominantly VLDBs, very large databases. I don't like the term VLDB because it sounds like some sexually transmitted disease, but very large databases have tended to be my thing. I started off as a developer, as a Forms 3 developer way back in like 1992, and I've been a PL SQL developer, I've been a database designer, a performance specialist. I've never really been a true DBA. If people ask me about backup and recovery, that's not my thing. I'm a development DBA. I look at the design of databases, making them perform well, using the technology available, working very closely with development or even being in development. So that's what I do. And I've swapped between database development and DBA type work over the years. I'm based in the UK, I'm English, I like cats and genetics and beer and drinking tea, and the IT was all a bit of a mistake, but I turned out to be quite good at it. I've written one book, or helped write one book, on real-world SQL and PL SQL with several much better people than me, like Arup and Helly and Brendan and Alex. I'm an Oracle OS director, and I'm a member of the Oak Table Network. Okay, that's enough about me. So, just a word of caution right at the beginning. I'm going to talk about diagrams. There's no slides full of words. You can send messages to Yalim as we go along, and he'll try and send them on to me. This is an introduction talk, so if you've got some deep questions about how the internals of blocks are structured, this ain't the time for them. But if I'm saying anything you don't understand or it doesn't make sense, feel free to ask questions. If this is all new to you and some of it goes over your head, don't worry about it. I find that these things need 1 or 2 iterations to really stick in your head. This will be one of them. If you don't get hold of it, next time somebody tells you about this, it will stick in your head. If you want to contact me directly, you can do. My email's on the screen at the moment. I'm on Twitter. I go to a lot of conferences and present, mostly in the European area. I'm easy to find, I'm easy to contact, and I'm a reasonably friendly guy if you want to ask me questions. Just one thing, this is an overview talk. I am going to tell you some lies. I'm going to cover over some of the complexities. It's a bit like learning about astrophysics at school when you're about 14 or 15, and you learn about there's the sun in the center of the solar system and the planets go round and how gravity works. And you have to learn that before you can start thinking about more advanced things like what are the nuclear processes in the sun that makes it hot, and how does Einstein's theory of relativity change the orbit of satellites and their signals to Earth as they spin round, which you would never try and teach at that level, but you need to know the basics to go into the details. So this talk is all about those broad brush general truths and realities of the database. There are always lots of gotchas and caveats, but if you've got the basis right, all those caveats make more sense, and in fact all the advanced features of Oracle make more sense once you've got these basics together. Okay, so what is an Oracle database? This is almost one of your standard pictures of an Oracle instance. So a database is often an Oracle, it's the instance. This is what lives on your computer, on your server. So you've got your server, and within there you've got a chunk of memory allocated to the Oracle instance. And you've got a set of server processors, Linux, Unix processors, that do various things. Now I could go through and talk about all the different Linux processors and what they do, but you don't need to know, not to begin with at least, and in fact you shouldn't really care. All you really need to know is that there are a lot of these processors, and each one does a specific thing within the Oracle database. So SMON is the system monitor, that makes sure that all of the internals are working. PMON is the process monitor, that checks all the Oracle processes are okay. The checkpoint process occasionally makes sure, quite regularly makes sure all the data is pushed down onto storage. You don't really need to know anything more than that there's all these processes working away. And every time Oracle introduces a brand new big feature, they tend to introduce a new process to handle that. So Oracle is built up as a set of processes. They all run the Oracle software, They just all do slightly different things. And all those processes run on your server. The other part of the instance is this chunk of memory that's allocated. And within there are several key parts. There's the PGA, which is the private global area, and the SJ, which is the shared global area. So the shared global area is where things that more than one user are going to want access to go. The biggest chunk of this is the buffer cache. So every time you read data, table data, index data from storage, it goes into the buffer cache. And the idea is that if you've read the data, somebody else using the system will probably want the same data at some point in the near future, so Oracle caches it and keeps hold of it. The other big cache in there is the library cache. Whenever you run a SQL statement or a PL SQL statement or a package, it gets put in the library cache. Again, because the idea is that if you run a SQL statement, it's probably part of the standard application, it's going to be used again soon. So Oracle caches it, and it doesn't have to keep doing this thing called parsing it all the time, it can just reuse it. So there are other components in the SGA, but the main ones are the buffer cache for the data and the library cache for the SQL and PL SQL. The PGA, the private global area, this is the work area for each user in effect. So when your query is running and the information is being generated, your SQL result set is being generated, it's put into the PGA. And if you're doing big sorts of information, it's done in the PGA. Nobody else sees that. It is purely yours. Strictly speaking, the PGA is not part of the Oracle instance. But you can't run Oracle without it. So I always think of it as part of the Oracle instance. Now this is a nice simple one server with one database running in it, one instance. You can have something called RAC, Real Application Clusters, which is where you have more than one physical server and the same database runs in each one and shares information between them. All of the processes I talk about for the rest of this presentation are pretty much the same. Talking about what RAC is in detail now is just going to confuse issues. All you need to know is that Oracle can run the same database across several servers for extra power and extra resilience, and it's a pretty cool feature, but it is an extra cost option. You can, of course, run more than one database in one server, more than one instance. You can run several. A problem with running many different databases on the one server is all of these processes. Each individual database has its own SMON process, its own PMON process, and all the other 60, 70 processes running, which is why running 20 Oracle instances on one server is a bad idea. And Oracle 12 introduced this thing called pluggable databases, where you have one central database and several can be plugged underneath it. Again, this is an extended feature of Oracle. It's becoming the more common thing to do, but it's still fairly niche. If you know you're going to use pluggable databases, then you'll need to go and have a little bit of a look into that. So that's our instance, that's what's on the server. The other side of things is the storage. And there are two main areas on the storage. You've got your database files and you've got your redo logs. Now you're probably all thinking that your database files are the key thing, but they're not. The key thing is actually your redo logs. Why? Because they are the golden truth of what's happened to your database. Whenever you change anything in memory in the database, whenever you change a block of data, it gets written through a process called log writer, and it gets written to the redo logs. And that is the thing that means that it's going to persist. That's the thing that when you do a commit, Oracle says, okay, I've saved that information, you will get it back, even if you have a crash of the database. The log writer is the most important single job running on an Oracle database, and it's constantly pushing all of your new data, all of your changes, even records of all your deletes into your redo logs. And there's only the one log writer. All changes you make to the database blocks are stored in your database files. This is where your tables and your indexes sit. And this is written out by these processors called the database writer. And there can be more than one. There can be 2, there can be 4, there can be as many database writers as Oracle feels it needs to start up to handle the workload, or a DBA specifies needs to be run as a minimum. So there could be many of these working away. A key thing about the database writer is it's lazy. By that I mean it doesn't write the information out immediately. When you change a record in a table, in the block buffer cache, and that information is written out to the log writer, it isn't necessarily written out to the database files immediately, because it can afford to delay slightly. It can afford to bunch up all the writes and do them in one go, which is more efficient. So you've got your memory, you've got your storage, and the thing that does all the work is a set of things called Oracle server processors. In effect, whenever you log onto an Oracle database, you as a user get given an Oracle server process, and that Oracle server process does everything for you. You as the user have no access to these files, you have no access to this memory, to these redo files or to the memory. Even the DBAs generally don't have much access to what's in the database files, in the redo logs, and in memory. They ask server processors to get their information. You, in fact, are over here. You're outside of the database, and the only thing you communicate with is the Oracle server process. I like to think of it as it's like a restaurant. The whole Oracle database is like a restaurant, and the Oracle server process is your waiter. So you go to the restaurant and you want a nice meal. So the waiter comes over, you ask the waiter what you want, the waiter goes and takes your order, and then the cooks and the commis chefs and the kitchen staff, they all work behind the scenes to make your meal for you, and they use the raw ingredients, which is the data on disk. They put it all over into the kitchen and cook it in the buffer cache and do the prep in the PGA area, and then the Oracle server process brings your information to you in the form of a result set. Do you care what the cooks do? Do you care if there's a separate pastry chef or not? No. All you do is ask the database, you ask your waiter for your nice chicken masala dish and wait for it to turn up. And to a large extent, that is the Oracle database. It's a big black box that does what you need. However, we're all technical people. We want to know more about what's in that big black box. So now I'm going to talk about the log writer, because as I said, it's the most important thing. Now before I mention that, you'll notice my buffer cache is now called the block buffer cache. This is not an official term, but I want to make the point that Oracle doesn't put rows into the buffer cache. It doesn't put columns, it puts blocks of data, 8K blocks of data, and it works on those. And I'm going to explain more later on in this talk why blocks are so important. But it is key to understand that when you are working on information within the database, you are working on blocks of data. Blocks of data are changed, and it's blocks that are read and written from disks. However, every time you change something in the buffer cache, that change gets written to something called the log buffer. And the log buffer is a circular piece of memory. And what gets written isn't the block, it's not the row, it's called a delta. It's a description of the change. So when you insert a new record, a description of how that record is structured is written to the log buffer. When you update a record, a description of how to do that update, that change, is written to the log buffer. And all of these Oracle server processors are constantly feeding information to the log buffer. Now this groups all the information together, and this one process log writer then writes the contents of the log buffer out to the online redo logs. Now these are your storage. You have to have at least 2 files, 2 online redo logs. And you usually have 3 or 5, you can have 7, you can have 4. It just seems to be common that you have 3 or 5. And what Oracle does, what the log writer does, is it writes all of the changes into this first file, this online redo log. When that one's full, it starts writing to the next online redo log. And when that's full, it starts writing to the next online redo log. And then it will wrap round and start with the first one again, so long as it's ready to receive data again. I'll come to that in a minute. So the data is written cyclically to these online redo logs. And these are vital, because when you commit, when you issue a commit statement to Oracle, what Oracle does is it makes sure everything has been written to the online redo logs on storage. And only once it sees that it's written there, does Oracle give you, that the record has been committed. It's not gone to the disk, it's not gone to the storage for the tables and indexes, it's gone to the online redo logs. Now very often, these are duplicated. There'll be 2 or 3 or 4 sets. And it's absolutely vital for safety of your database that you duplex or triplex the online redo logs. So you have 2 groups or 3 groups. And the log writer will write to both of them, or all 3 of them, depending on how many you've got. And the reason that you always have more than one group is one of these files could get damaged. It could be accidental. It could be that you've had hardware failure. It could be malicious, actually. But the idea is if there are 2 sets, it protects you against that single point of failure. So the log writer does write out to 2 or 3 sets at the same time. And there's almost no overhead by having multiple sets. Now you can do operations in Oracle with something called no logging. So bulk operations like creating one table from another, or batch loading a load of records through SQL Loader. They can be done so that the information is not written to the online redo, or at least not the full information, there's just outline information. And that speeds things up. And it's a common trick that people use to speed up batch processing. They'll use no logging. I hope you can see that this is actually quite a dangerous thing, because if you lose these online redo logs, your database can't recover if there's a problem. So you really should avoid doing tasks that are no logging. Now sometimes DBAs will say, well, we can skip those no logging activities when we do a database recovery. But almost no site I've been to keeps track of all of the no logging activities that they do, so they don't know exactly what they've lost. So I do recommend that you don't use no logging unless you've really got a very, very great need for it and you fully document the facts. So I've indicated these online redo logs are used to redo everything in the event of a database crash and recovery. And if you have an instance failure and the instance starts up, Oracle will know what's been committed, been put to these redo logs, and it can use the latest entries to redo any strange damage that's happened to the database files at that crash time.
Martin, may I ask a question?
You can.
Yeah, I'm asking this question. At some point in time, I looked for a way not to log an update statement.
Mm-hmm.
I wasn't able to find a way. Is that true? Like there is no way not to?
Yes, so individually insert, update, delete statements, merge statements, you can't stop them from logging. The only thing you can stop from being logged, really, are bulk operations.
And that's inserts, really. Bulk operations, inserts.
So if you're doing a create table as select, there are only certain bulk operations that you're allowed to disable logging for. Nearly everything else, all individual insert updates, even if you're doing a bulk insert for PL/SQL, they will be logged and you can't stop it logging. Because the logging is an intrinsic thing that Oracle does.
Okay, so there is really no way to turn it off by stable space or by table, or just no way, except very few exceptions.
Yes, because if you think about it, if you could turn it off for individual statements, When you did a commit, which was, say, for a banking transaction where you have to record 7 or 8 things in different tables and you do it as a transaction, and you'd managed to set some of those updates or inserts to not be logged, if you were trying to do a recovery of the database or a restore of the database as a normal backup recovery operation, they wouldn't be, only parts of it wouldn't be in the log writer, in the redo logs. And so Oracle wouldn't be able to replay those back.
Yeah, of course. But, I had this odd situation where I just wanted to turn them off. But I can't. I literally can't.
You can't. Okay. So you've got your sets of online redo logs, and these are so important that you nearly always have an archiver process which archives them off to other storage. So every time a redo log is filled, the archiver process picks it up and bulk copies it to your archive redo destination. And because it's a bulk copy of the whole file, this is very quick. So the archiver can usually keep up with the generation of the online redo, especially if you have 3 or more members in the group. And these archive redo logs are just generated, and you can just think of them being generated over time, going further and further back in time. And if you keep all of your archive redo logs, you can actually recover your database at any point in time. Whenever you do a backup of your database via RMAN, then what you're essentially doing is saying, here's a copy of the database, and Oracle has to have the archive redo logs for that period so it can regenerate any changes happening during the backup. And theoretically, you could take the original backup you did when you first created the database and apply all of the archive redo logs to it. It will bring it right up to date. Now that might not be true if you've done an Oracle upgrade, so gone from version 11 to 12. I can't say I've tried it in about 20 years, but barring major things like that, during which of course you would be taking plenty of backups, your archive redo logs are what are key to you recovering your database. And in fact, the online redo logs are key to things like setting up standby databases. Another advent, you can actually mine the online redo logs and the archive redo logs for changes if you've got the correct tools to look for when changes happen to the database. So the online redo logs are used by Oracle extensively for high-end features of the database.
Martin, I received 2 questions, especially this one is asked in different variations, but Danny asks, is there an extra write latency involved if you have more than one redo group?
No, not really. So long as the redo log groups are on similar storage, then there is not really an extra write latency by having more than one, because Oracle writes to them asynchronously, and it will wait until one of them has returned before it continues.
Yeah, that was another question.
Yeah, if you lose an online redo log group, Oracle will put warnings in the database alert log, but it will keep going so long as it's got one left.
Jess asks about the no login clause in the table syntax. The create table syntax is a no login clause, but it doesn't really do what it should do, right?
No, what that does is it means that any bulk operations that are carried on it which can be done no logging will be done no logged.
Yeah.
But all normal standard DML is logged. If you don't want your database changes to be logged, then use a different database technology, which doesn't do this sort of thing so well. And you lose your ability to recover so well. So I'm not sure exactly what the story is with MySQL anymore, but certainly a few years ago, part of the reason MySQL was so fast is because there was just no concept of really logging all the changes in this way. It just relied on changing the underlying files.
Okay, there are many questions, but I'll skip them, otherwise
we'll never get there.
Yeah.
Okay.
Because I know this is a hot button. This redo logs and log buffer is a hot button for a lot of people. If we have time, I'll revisit the question.
Indeed. When we get to the end, then we can come back to it. But yes, I do need to move on a little. One last thing to mention, I say there's only one log writer, and people have asked me why is there only one, and I think it's to keep it very simple. The way to do something very quickly with computing technology is do it in a very simple way. As soon as you have two processors potentially writing information to your online redo logs, they'd have to be communicating to each other, adds more complexity, they have to check with each other all the time. So having one process keeps it simple and keeps it fast and reliable. Now in Oracle 12, two new processors were added, LG00 and LG01, and these are kind of helper processors. So there's still only one log writer, but it passes some of the workload onto these. Now the documentation suggests you can increase the number of these helper processors. I've never seen more than two, and people who I've asked who've tried changed it said, nah, it just seems to be that there's two helper processors. And that might be different in 12.2, I've not checked recently. But the take-home message is for all previous versions of Oracle, and even still for 12, there was effectively just one log writer process.
Yeah, that was actually one of the questions.
Okay, so that's one area of the storage covered. The second area is the database files, what most of us think of as the key database. Now, I've just used your standard generic cylinder things to represent storage. First of all, Oracle doesn't care what your storage is. It doesn't care if it's spinning disk. It doesn't care if it's new SSD type storage. It doesn't care actually if it's tape. You can actually set up Oracle to use tape as long as it's read-write. And I've worked on a system a few years ago which had a massive amount of its database stored on a tape system. It just has to be storage that Oracle can read and write. Within the storage, you create these table spaces. I'm sure nearly all of you are aware of this. So you've got three table spaces here. The yellow ones, system and sysorgs. They are special table spaces. Oracle creates them for you when you create the database. And Oracle puts its internal objects in there, its information about its tables, its views, its code, its internal structures, users, grants, privileges. And monitoring information and extra information tends to go in sysorgs. You can put your own objects in system and sysorgs, but you really, really should not. And it would be a very bad thing to do, because they're there for the internal use of Oracle. Never put your own objects in system and sysorgs, and never change anything which is in there, because these are the Oracle internals. If you go playing around with them, Oracle support might turn around and say, well, guess what, you've just broken your support contract, you're on your own. Do not mess about with anything in those table spaces, but they are just normal table spaces. Here we've got a user-created table space called ORDData, and it's just a file on storage. As far as Oracle is concerned, it's just a big file. And these table spaces are made out of these blocks, and these are the database blocks. And when you create your database, you state what the database block size is going to be, and it will be 8K. From Oracle 10 up to 12, it's 8K. You can change that. You can change it from 2K up to 32K. And I would strongly suggest you don't. Not unless you've got a very good reason. Now, if somebody's telling you to change the default block size of your database, ask for proof. If they just say, oh, it's because I've got this theory, that's an opinion. That's not proof. If you're going to change something fundamental like the block size of your database, you need a proven, proof of concept, been tested properly reason to do that. The reason being, A, 8K just works very well. It's good for OLTP, it's acceptable for data warehouses. The other thing is, Oracle does all of its testing on 8K block sizes. Now, in here, you've got these things called extents. Extents are chunks of 8K blocks, and these are basically where your tables and indexes exist. So when you create a table, it will consist of a number of extents, which itself consists of 8K blocks. We used to worry about this a lot in the olden days. So when I first started off as a DBA type person, I came up with ways of creating and managing the extent sizes. And it's disappeared as a problem because Oracle now looks after it for you, and it does a very good job of it. You just don't need to worry about it unless you're creating a very, very large database of ELDB, and you need to create fixed extent sizes so it just performs slightly more efficiently. If you're creating a VLDB, then you'll need to look up creating table spaces with fixed extent sizes and understand what's going on. So, just get rid of some of the clutter in this diagram. On another disk, we've got two more files. One of them is also for the all data table space, and you can have as many files as you like, and the maximum size is 32 gig per file. And we've got another table space here, which I call ORD IDX, which is where I put my indexes. Now, you don't have to put indexes in different table spaces. You can put every single table and index that you like in the one big user-defined table space. But I still split them out for three main reasons. One of them is old, and I'm used to doing it because we used to do it for slight performance reasons, which have disappeared. Another reason I do it is so that if I ever want to use something called transportable table spaces to move chunks of the database around, it helps if all the tables that are related are in a small number of table spaces. And the reason I still have separate index table spaces is every now and again I will lose a data file. And if the data file is only for the an index table space, you don't have to mess about recovering it. You can just recreate the indexes that you've lost, recreate the table space and recreate the indexes. It's happened to me maybe 3 times in 25 years. But as it costs me nothing to set up separate ones, I still do it. And I just like almost the self-documenting nature of doing that. But there's no need to do that really. On this other piece of storage, we've got another table space, build data. And this is a big table space. It holds a lot of data. And you can create something called a big file table space. And the file underlying it can be more than 32 gig. It can be as big as you like. And it's quite useful to do that for very large table spaces. So these are standard file table spaces, and that's a big file table space. Any questions about data files and blocks and extents?
What are your views on having a table space for lobs?
It's a slightly complicated question, that, because you've got your lobs and you've got your lob overflows and things. I tend to put all of my lobs, if I'm using overflow segments, in a different table space. And in fact, because I'm usually doing that with partitioning, I'll have a separate table space per partition as well to enable the lifecycle management. So if you're dealing with lobs, you're dealing with large quantities of data as a rule. So therefore, I will create a separate table space. I will have the overflow segment for the lob go into those separate table spaces. And if I'm partitioning that table, I will also have a set of table spaces per partition. That's given that I don't go mad and have daily partitions or hourly partitions. Okay. So we've got our storage and we've got our instance, okay, which if it's a single server, instance and database are almost interchangeable terms. I didn't say that earlier. I do tend to use the two to mean the same thing, which is a single instance database. So how does the data get from the storage into the block buffer cache? It's actually done by your server process. So when you run a SQL statement, then your server process will look in the block buffer cache for rows that it needs, and if they're not there, it will go to the storage and get the block holding the row. So remember, the block buffer cache holds blocks, not rows. So when you run a SQL statement, the server process, you'll probably first go to the system table space and get some information about the SQL statement that you're running so it can parse it and execute it. Because all the information about your tables and your indexes, they're all stored in tables in the system table space. So Oracle gets that information, pulls it over into the block buffer cache and works on it. It will then go to the data segments and start pulling information into the block buffer cache. Because the only place that any computer program can work on information is in memory. And with Oracle, it's the block buffer cache. The server process might now need some information from a table in a different table space on different storage, and again, it just goes and gets it and pulls the information over. So the server process, your waiter in effect, goes and collects the information from storage, puts it into memory. Now, if you've changed a record, so we're going to change this record, I think it is. Oh, forgot to say. So sometimes Oracle won't read a single block. It'll read a large number of blocks. And I will come back to this in a few minutes. But Oracle, if it knows it's going to read a lot of information, usually doing something called a full table scan, it will read that in one big chunk. That tends to go into the PGA. Again, I'll come back to that. So if I decide I'm going to change this record, this block, it doesn't get written back by the server process. It gets written back by database writer, as I mentioned 20 minutes ago. And it's done, as I said, in a slightly sort of lazy way, because the important information that is needed when you commit is written to the online redo logs. So the database writer realizes that blocks have updated and copies them back to storage. Now, I've shown the block moving. It actually does leave a copy in the block buffer cache, but it does update what's in the storage. If you create a new block, so I've just created this new block here, then eventually, usually within 3 seconds, the database writer will go and put it in an extent in the correct data file for that object. And it's the database writer that does that. And there can be multiple database writers constantly checking for things that have changed in the block buffer cache and writing them out. So if you delete a record, that counts as a change to a block, so that changed block will get written out to storage. And every 3 seconds, or after a certain amount of activity, the checkpoint process will kick in and make sure everything's been written out to storage cleanly. There's one table space I've not talked about yet, and this is the temp table space. Again, it's made up out of AK blocks, unless you change the size. And this is used for stuff going in your private global area. So as you're creating a large, the results of a very large select statement, that will accrue in your PJ. If it gets too big, Oracle will temporarily store it in the temp. Again, the server process does this for you, your waiter. If you need to sort information and it won't fit into memory, Oracle can write it to temp, then bring it back into your PJ via the server process. You don't touch, personally, you don't store anything in temp. Temp is purely there for the internal purposes of Oracle to put in sorts and large data sets that it's temporarily working on. Now I'm going to just touch on this AK block size thing again. You can actually create a table space with a non-default block size. So you can have your default 8K block size and you can create a table space of 32K. And I've seen this done by people who think, oh, I've got this really big table, it'd be a very good idea. Don't do it. Because if there's anything worse than changing the block size for your database, it's mixing block sizes for your database. It might seem like a good idea, but it doesn't sit happily with the block buffer cache. You actually have to set up different buffer caches for the different table space block sizes. The reason that you can do this, that you can create table spaces with different block sizes, is so you can transport table spaces from one database to another, where they have been created with different block sizes. And whenever I've been in the situation of doing a transportable table space of, say, 32K block table space into an 8K block database, first thing I do is copy all the data out into a new 8K block database, table space. Any questions on how Oracle moves information between storage and memory? Okay. So, just to change tack slightly, you want to find a record. Very common thing to do when you're querying a database, of course. This is the record you want, and it's in this big table. And you've got no indexes. How does Oracle find the record? Well, there's no index. There's no way for Oracle to know where that record is, so it has only one option, which is to read the whole table, do a full table scan. So it gets the first 8K block and it reads it in, gets the next 8K block, reads it in, gets the next 8K block, reads it in. If anybody's thinking this is very inefficient, you're right. If you're thinking that I'm lying, I'm lying. When Oracle does a full table scan, it actually reads big chunks of blocks. A full table scan is a multi-block read. So it chunks through the data very quickly. So it will grab, usually, enough blocks to equal 1 megabyte and reads it. And it actually puts it into the PGA, the Process Global Area, not the block buffer cache. And it does that, and it gets the record. And it will actually keep doing that because it has no idea how many records you're going to find. You might think, well, what if I've got a unique index on that record? You'd have an index then. So, or a unique constraint, I should say. If you don't have an index, whether that index is created by a constraint or not, it will full table scan. But it will do it in big chunks. So Oracle reads either 8K blocks or 1 megabyte blocks of data from the database, and it reads usually chunks of 512K or whatever to the redo logs. And this is important when you're talking to your storage admins, because Oracle's often reading either 8K blocks or 1 megabyte blocks, and they'll say, well, you're not stressing our storage, you're not moving as much data as you could, but you're seeing problems with the storage not responding fast enough. It's because it's got to read in these two sizes. And what is often the problem is the storage can't do enough operations a second, I/O operations a second, because it's reading bits of 8K. Now this is one of the arguments for going to larger block sizes, but the problem with going to larger block sizes is every time you read a record, you're using now 16 or 32K in memory for the one record. 8K seems to be a nice balance between those. Now I've said when you do a full table scan, it goes into the PGA. The problem with that is that if you need to full table scan again to find that record, you don't have access to what's already been put in the PGA if you're a different user. Even if you're the same user, it will have to do that full table scan and put it in the PGA again. It's not being cached. The reason this is a lie is Oracle knows that if it's a relatively small table, it will put those multi-block reads counts into the block buffer cache. What counts as a small table? Well, that varies. It's not always easy to say. But generally speaking, if you're doing a full table scan of a large table, it won't be cached. And if you think about it, that's what you want. Because if you're doing that, you're probably doing a data warehouse type query. You're querying a huge amount of data. You don't want to fill your cache with that. You want your cache being filled with data you use all the time. And if you are really needing to fully scan very large tables all the time, then you probably need something like Exadata to help you with it. Okay, so that's getting a single record with no index. We usually create indexes to help us access individual records or sets of records. So this is our index, and I've drawn it as a triangle, and here's our table over here. If you want to get a record, let's say you want to get all the records for a given patient ID. The ID is unique. Every single patient has a unique number allocated to them. So what Oracle does is it goes to the relevant index, and it goes to the root block, and it reads the root block. And that will say that this ID is represented by this block here in the next level down. And that will say this ID is represented by this block here in the next level down. As you can imagine, that one says this ID is represented by this block in the leaf block level. There's an actual single entry for the patient ID. It's the row ID it's called, and that points directly to where the record is in the table. Now the root block, Oracle always knows where that is. When you create an index, Oracle knows where that root block is, and it doesn't change. As you add more information, you'll get a set of leaf blocks created. And as you create even more information, that's when you in effect get the first level of the branch block created with the leaf blocks below. In my diagram, that's happened 3 times. So this is a pretty big index. So you've got your root block, 0, 1 or more branch blocks, your leaf blocks, where the actual IDs, the actual entries in the index are contained, and those row IDs point direct to the location of the record in the table. Now, if I had to full table scan that table, it would take, depending on the size of the table, several hundred, several thousand, several million IOs to get the information. With this index, it's 1, 2, 3, 4, 5 to get the record, and then that information gets put in the block buffer cache. And the reason indexes are so powerful is it looks here like that the branch level is holding 3 or 4 times the information the root block does, and the branch block 2 is holding 2 or 3 times the information of the branch level enough. It's not. It's holding hundreds of times more information. So the root block can reference, depending on what you've indexed, whether it's an ID or whether it's a set of varchar 2s, it could be referencing 100 entries, it could be referencing 200 entries. One entry there will reference up to 200 entries there, which will reference up to 200 entries there, which will reference up to 200 entries there. Every time that the index grows by one level, the amount of information that it can actually index doesn't double or quadruple, it increases by sometimes a factor of 100 or 200. And this is why no matter how big your table gets, you'll probably only see an index get down to a depth of 4 or 5. Especially if you've used partitioning, if you've got the partitioning option, split up your tables using that, you will probably only get a depth of 3 or 4 for your partition indexes. And as such, to find a single record will never be more than 1, 2, 3, 4, 5 IOs. That's why indexes are so powerful. Now, a more interesting situation is where you want to get several records for an entry. So let's say this is it's a hospital system again, and I'm looking for my name, Martin Woodlake. Now, actually, with my name, there's not going to be many people on there called Martin Woodlake. But if I'm John Smith or I'm Singh Patel, there's going to be hundreds or thousands of entries for any given hospital system. So you give it the values, Martin Woodlake, it'll look in the root block, go down to the branch block, go down to the branch block, get to the bottom, and it will find the first entry. And it will go to that entry in the index and look up the block in the table. It will get the next entry and look up the next record in the table. So it just scans along the leaf block until either it needs the next leaf block or it's run out of entries. So to collect these 9 entries, it does 1, 2, 3, 4 reads, 5, 6, 7, 8, 9, 10. Back to here, then reads those. So it's still efficient, but the records are scattered all over the table. And that's why a range scan can be more or less efficient. Because if the records really are scattered all over the table, each time Oracle goes to the table to get a block, the only record that it needs for that range scan, there's only going to be one in that block. Whereas you can set up your situation, set up your database, design your database so that related records are generally in the same block. And that can make a big difference for the efficiency of this range scan. I'll touch on that again in a minute. So, a question that's commonly asked. For a given query, is it better for Oracle to do a full table scan, or is it better to do an index range scan and dot around this table to get all the entries required? And when I've got a physical audience in front of me, I ask the question, what's faster, full table scan or a range index scan? And very few people are brave enough to answer. And the reason is, it depends. It really does vary a lot. As a very rough rule of thumb, if it's a very small table under a few hundred records, it's probably faster just to grab all the records in all the blocks in the table. If it's what I'd think of as a normal table with several thousand to several hundreds or millions of thousands of records, a full table scan is going to be faster if you need more than 1% or 0.1% of the records. If you need less than that, then an index range scan is going to be faster. And the larger the table is, generally speaking, the smaller a percentage of the records that a query needs is going to be more efficient for a range scan. So if you've got 1 billion records in a table, it's probably really is going to be anything more than 0.1% of the records. You might be faster doing a full table scan. Some of you might be using Exadata. Now with Exadata, I'm not going to go into the details of Exadata, but Exadata has a lot of intelligence at the storage level that makes full table scans much more efficient. Now it doesn't mean that indexes are no longer valid and useful, it just means your indexes have to be even more specific to be the best option to use.
Robin has a question. He asks, what are the pros and cons of B-tree and hash partitioning indexes? Is this something you want to get into now, or?
You mean B-tree? Hash.
I just.
You only have B-tree and binary bitmap indexes in Oracle.
Yeah, I didn't understand what he meant by hash partitioning indexes, but I figured I asked.
There is sometimes discussions about, are you better to index or are you better to partition the table and just do full table scans? And that's a very complicated question to answer, because you have to really understand what your application is trying to do most of the time. So you could imagine a system which holds 5 years of data. So instead of indexing the date, you could just actually partition the table on date. And so you'd actually be happy just scanning a date's worth of information every time you need to find your records. But that really depends on how your application is going to access the information. There are 2 main types of index in Oracle. There's the balanced B-tree index, as we call them, which I'm indicating here. And there's also this thing called a bitmapped index, which is a totally different structure, and it's useful for very large sets of data that do not change very much. Now, some people sometimes say they're very good for low cardinality columns, i.e. where you've got male, female, or yes, no. And that's an urban myth. That's been disproved so many times. They're actually good for when you have a smallish number of distinct values. So, say 20 different status indicators or something like that. And they're very good when you can combine several of these low cardinality columns together. Because with bitmapped indexes, you can combine index information together. With B-tree indexes, you can use one index and one index alone. I'm not going to go any further because that is quite an in-depth discussion. But if you have a very large data warehouse and the data is static, i.e. you're not updating and changing it all the time, binary and bitmapped indexes can be very useful. Any other questions?
There are many, but let me just, hi Arup Nanda is here. So let me ask Arup's question. I apologize to everyone, I'm skipping some questions simply because of time constraints, because there are almost 300 people online. Arup says, hash partition indexes are simply B-tree indexes partitioned by hash.
Okay.
Divide the entire index segment into smaller subsets. So
okay,
that the index will be much faster.
So yes, that's all part of the partitioning option, which I don't really discuss in here. The concept is that yes, you can split up your table into smaller chunks, and with hash partitioning, it means that if you're accessing the record on the ID that's used for the hash partitioning, it can go directly to the correct partition. Yeah. We can always trust Arup to see straight to what the answer is. So, I just want to briefly cover this idea of what's in a block, because it seems to be disappearing as something people consider when they're thinking about their database, whether it be Oracle or not. So here's my 8K block. It's full of rows, and there's my relevant row. So when I go and select my row, this whole block comes into memory with the one row I want. Now if every time you go and select the row or rows that you want, it comes with a load of other rows you're not interested in, or at least not interested in at the moment. That means that your block buffer cache is going to be full of rows that you're not using, that you don't want to process. And I call this collateral data. And it's effectively wasting your block buffer cache. It's reducing your buffer cache down to 5% of what you've actually allocated. If you can move to a situation where you're doing this, where when you go collect a row, it's surrounded by other rows that your queries need, then that means that each 8K block is holding a lot of information that your database is working on. Now it's a more extended, more advanced topic to really go into how you do this. I actually do a whole presentation on an hour on how to do this. But you can use things called index organized tables, where the information is actually stored in an index. You can physically sort your data, or you can use partitioning to move you more to this. When you get a record in a block, it's surrounded by other records that you probably want to process that day and make your whole database more efficient. So it's actually worth thinking about, if you do database design, how you actually physically structure your tables to gather together relevant records. And a common way to do this is partitioning your database, the big tables, by date. And 99% of your processing is on today's data, or yesterday's data, or this week's data. If you've done that, then you effectively move to this situation where when you collect one record, then other records you're going to process are going to be in that block because they're all for the same day. I won't go any further than that. Right, slight change in topic. I'm going to tell you how Oracle parses and executes a SQL statement. So we know how information is stored, we know it's the server process collecting it and the database writer putting it back, and we know about the log writer being the key thing, writing your redo logs all the time. But how does Oracle actually run a SQL statement? Well, when you issue a SQL statement, the first thing Oracle does is it makes sure that the syntax is valid, i.e. the select, insert, update, delete, merge is where it should be, the from is where it should be, that the actual language is correct, that it can understand the statement. The next thing Oracle does is semantic check. So are the columns that are referenced, are they actually in the table that I'm looking at? And if the table isn't stated in the select clause, is the column only in the one table, so it can actually identify which column is being referenced. So it's making sure not only is the statement in a language it understands, but it's structured correctly, and there's no confusion about, there's no ambiguity about what the statement is. The next thing is Oracle looks for the SQL statement in the library cache. And it does this by taking the text SQL statement and creating a numeric hash value, which sometimes is represented as a hexadecimal value. It creates a value based on the actual letter-by-letter SQL statement. And it checks to see if that's already been seen. And if it has, Oracle knows that it doesn't have to fully parse it. Why doesn't Oracle do this right up here as soon as you first issue the SQL statement? Well, it's because it might not be a valid SQL statement, so it'd be a waste of time. An impact of this hash value is if you issue a SQL statement and you issue exactly the same SQL statement, but you change the case of, say, the select word, or you add extra spaces in the statement, then it won't have the same hash value, so it will get parsed again. If your SQL statement is embedded in a block of PL SQL, Oracle actually does strip out a lot of that extraneous stuff, so you stand a better chance of getting a perfect hit. But basically, your SQL statement has to be character for character the same for Oracle to be able to use a previously calculated execution path. The next thing Oracle checks is, has this SQL statement been run in the same way? Now, Oracle gives you a lot of flexibility to change lots of things about your session. So you can actually say to Oracle, I want you to run this session as though it's using the Oracle 11 optimizer rather than the Oracle 12 optimizer. Or you can tell it to use a different set of values for its memory settings. And Oracle does actually check that you haven't changed any of those things. One of the problems with Oracle giving us so much flexibility over what we can do is that Oracle creates a little bit of a problem itself that it has to constantly check that nobody's done that they haven't changed their actual environment that they're running the SQL statement in. So hopefully now Oracle has a SQL statement that it understands, maybe it's seen before, and it can parse and it can optimize it. What does Oracle do when it optimizes a SQL statement? First of all, it rewrites it for you. It transforms it internally into different layouts that may or may not be more efficient. So it might take subqueries and merge them into the body of the query. It might take with clauses and merge them into the body of the query. It might actually do things like transitive closure, where it knows if A equals B and B equals C, A equals C. So it does all these things before you. It creates logically identical versions of the SQL statement and tries to see if there's a better way to execute it, or to understand it, I should say. Once it's done that, it takes the statement and it looks at the table join methods and the table join orders, and it tries to come up with the best plan that it can. And it calculates the cost for each of these various ways of doing the executing the SQL statement. And the cost is basically Oracle's estimate of the number of logical or physical IOs it's going to do. And if you really do understand the cost-based optimizer well, and you look at the information available to it in the object statistics, table statistics, you can actually predict what the cost is going to be. But with every version of Oracle, this gets more and more complicated and hard to do. But it is just mathematics. It is just Oracle making a mathematical calculation of what it expects each step to cost. So having done that, Oracle then chooses the one with the lowest cost. Now, sorts cost, big joins cost, CPU processing doesn't really cost very much. So I've said, properly understanding the optimizer now is a big ask. I don't know whether Alp's still online or whether you agree, but every single version of Oracle gets smarter and smarter, and it makes the life of us who claim to be performance experts harder because it's getting cleverer. They don't add these extra confusions for no good reason. The optimizer team add these extra abilities because they've seen things in the real world and they're trying to solve a problem. But the end result is it's very complicated. But one thing I will mention is many of you have heard about hints, SQL hints, to cause the optimizer to do what you want. So use this index or join these two tables in the right order. Hints aren't hints, hints are directives. If a SQL hint can be followed, Oracle will follow it, no matter how stupid it is. And it also fixes that code in that path, so that if the data volumes change or if the optimizer changes, a valid hint will fix it in that path, so long as the hint can still be honored. So it kind of becomes part of your code base. So you have to wonder, do you want to add hints? And the other problem with hints, just to almost fly in the face of what I said, is sometimes hints that are valid simply don't work. And that's because it tells the optimizer to do something it's already decided 4 or 5 steps earlier in its calculating the path not to do. So there are situations where Oracle can decide it doesn't need to look at a table. It can look at the index and get all the information. So if you go and tell it to join the tables in a certain order, that hint may not work. So if you use hints, do be aware that you have to be a little careful with them.
Martin, Venki has a question, Venki Raman. He asks, reading and understanding explain plans is a big challenge, no matter how many books I read. Any tips?
Yes. It gets particularly difficult when you get parallel query. The only thing I can say is the only way to learn how to read an explain plan really is to write simple SQL joins yourself and slowly build them up and see how the plan changes. So rather than taking a 12-table SQL plan output and trying to work it out, start off by just writing your own simple 2-table, 3-table joins and working out. And if you look at a SQL plan output, it generally tends to be that you go down the slope of the plan to the first point where it comes back on itself, and you work your way up the plan until you find the next spike sticking out below it. That's the best way I can put it. But unfortunately, the only way to really learn how to understand SQL execution plans is to read things by Tom Kite, although he's now stopped, Jonathan Lewis, Arup Nanda, and practice. Now, if you've got access to SQL Monitor or one of the more advanced performance monitoring tools, it will show you how Oracle is using the execution plan as it runs and how information moves between steps. And that can be a great help if you've got access to it. I don't know if that helps, but it's the best I can give you at the moment.
Building the query helps. I think that's a good trick.
Yeah.
So instead of attacking the query with 12 tables and God knows how many joins, you can start from 2 tables and build it up.
Something I also do is anybody who's online who's got an academic background in IT, so they've done an IT-related degree, has at some point probably done entity relationship modeling, where you draw an ERD. I find if you draw a sort of ERD stroke table map of the query and how you think it's going to work, that quite often actually is the execution plan. Okay.
Kirk is asking if you're actually drinking beer during the presentation.
I am, because I have a reputation for doing this, and I didn't know that the webcam was going to be on, and I was going to take a photo of that and send it to my friends on Twitter afterwards. Yes. Damn, caught. Okay. Besides, it's at the end of the working day here in Switzerland.
It's true, Dan. Go for it.
Right, read consistency. When you change some information in the block buffer cache, when your SQL statement, you want to run your SQL statement, the Oracle server process knows it's going to change something. So I want to change a record, but the block is not in memory. I've got to get it. So it reads the block. So the Oracle server process reads the block. Now you change the information, and very quickly the change delta is written to the log writer. That's the first thing that's done, and when you commit, Oracle says, yes, that's committed as soon as it's confirmed it's been written to the redo logs. More slowly, that change will be copied back to disk via database writer. But that's not the whole story. There's 2 other things. There's this thing called the SCN clock, which is up here, and there's the undo table space. Now, when that record is changed, this Oracle server process checks what the SCN number is. SCN is system change number. Every time you change something in the database, the SCN ticks up by 1. So you can think of it as every time you change a record. It's not quite as simple as that in reality, but you can think of it as every time you change a record, the SCN ticks up by 1. And Oracle records that SCN with that record to say, this is the point in time when that record was changed. Oracle also writes the block as it was to undo. And this is so that if you decide not to commit the change, Oracle can pull the information back from the undo table space. There's another reason for it being undo I'm going to come to in a minute. But basically, Oracle is recording how the block looked before you messed with it. Now, I don't show it here, but this is a block change. This will also cause information to be written out to the log writer. So when you actually change a record in an Oracle table, the information gets written out to the log writer twice. One as the change to the original block, and one as the change to the block in the undo table space. Now this is how Oracle manages its read consistency. So read consistency is when you run a query, Oracle will show you the data at the very, very point in time as when you ran it, even if other changes are happening at the same time. And this is one of the golden things that Oracle and other ACID RDBMSs do, databases that promise to show you a consistent view. If you're running a report which takes 20 minutes to run about what you've got as stock in your warehouse, do you want it to take into account any changes to the stock in the 20 minutes it's running? Probably not. And if you do, how do you want to know that when the stock changed? And if you think about it, knowing about any changes since your query started depends upon whether the records affected are seen before or after that change. And that's how some systems work. They just show you the data in the table for each record as it gets there. What you really, really want to know is the state of play at the very, very point you ran the query. And if you think about banking systems and anything where money's moving or people's health is concerned, you don't want an inconsistent view of the data. You want an absolutely rock-solid view of the data. So read consistency is often overlooked, but it is absolutely vital. So you run your SQL statement, it gets parsed, etc. And the very second that it runs, the Oracle server process grabs the SCN at that time. In this case, it's 45678. It then starts collecting data. This arrow is not showing it, by the way, an order within the block buffer cache. It just indicates processing the query. So it gets the first block, and it has an SCN of 45123. Now that's lower than 45678. So Oracle knows that block's not changed since this query started. The last change is a long time ago. It gets the next block, 45007. Again, it can use that block. It's not changed. Next one, 45688. This has got a later SCN. This block's been changed since your query started. Something's happened to the data. Oracle copies the block in memory, only in memory. And it then goes to the undo, gets the information about that block, and rolls it back in time. And now it's got an SCN of 45422. It's older than when you started. It can use this data. Oracle goes to the next block. That's older. Next block. That's good and old. Next one. This one's changed. So again, Oracle copies it, applies the undo, and gets 45699. That's still more recent than when the query started. So more undo is applied, and Oracle will keep on applying the undo until it gets a version of the block that's old enough, that predates when your query started. In this way, everything that Oracle sees for your query is as it was at the point you ran the query, you started running the query. And that gives you your point in time view. Now, which one of these, every time you get a block, it's called a get. Which of these are consistent gets? People often talk about consistent gets. So which of these block gets is a consistent get? And the answer is, they all are. It's not whether Oracle has to apply this undo that makes it a consistent get. It's that Oracle considers whether it will need to do that. So the majority of consistent gets that Oracle does, if you ever see the statistics in the more in-depth information about Oracle processing, it just means it's considered having to roll the block back to a point in time, not that it actually has. Now, 99% of what we do as application developers, our SQL statements will all do consistent gets because we need that point in time. Any questions about that?
There are a bunch I'm literally half skipping some good questions.
Well, I'll tell you what, I'm considerably over the hour, so if I just plough through and get to the end of the presentation, then we can go back to the questions. Yeah?
Okay, yeah.
So, how does Oracle find the block in the SJ? I keep on saying this, Oracle checks for the block in the SJ, but how does Oracle do this? Now, I've had a couple of crazy ideas in my lifetime, my working time with Oracle. First of all, I thought CPU's fast, memory's fast, it just scans the block buffer cache each time until it finds the block. Well, that's silly, it doesn't do that at all. The other thing I thought was that Oracle might preserve an index-like structure of all the blocks in the SGA and look it up via that. And Oracle doesn't do that. It does this thing called a hashing algorithm, which brings us back to the earlier question about a hash, partition hashing. Oracle uses hashing a lot, and in fact, again, if you've got a background in informatics or IT, you'll know all about hashing. But for those who don't, this is a value. This is a pseudo row ID. It's not a real row ID, but I've got this pseudo row ID, and I push it into the hashing algorithm, and it will give me a number, and it will always give me that number for that value. I've got another row ID. Now you'll notice it's only different by one letter, and it just A goes to B. I put that through the hashing algorithm, and I get a number which is quite different. It's not one or more or less than the previous one, it's quite a different number. A hashing algorithm will always give you the same output for the given input, but it's not unique. There could be several input values which match the same output, but you'll always get the same output for the given input. Depending on how the hashing algorithm's been designed, you'll get 2 or 3 values, you'll get 20 values, you'll get 100 values. The idea is you get a small number of values. That value points to an actual physical location in the buffer cache, and Oracle then checks there, and it checks what blocks it's got hanging there, and if any of them are for the row ID you inputted, and in this case it is. And that's how Oracle quickly finds whether your block is in the block buffer cache. And the reason I've put this in at the end of this presentation is so few people have ever had this explained to them. This is how Oracle finds stuff in its block buffer cache. So the last thing I'm going to mention is I've given you this introductory talk. I hope it's been useful. I hope I've not made things too confusing. I know I've covered an awful lot of information, but this has been recorded. You can go back and look at this as often as you like. And I've talked a little bit about SQL, a tiny bit about hardware, something about internals. And I found that over time, you just go around in this spiral and you learn more and more. So I've taught you a bit about some of these things. So you could probably now go and understand better how database recovery works, because you now understand about redo logs and archive redo logs and undo. And if you learn more about recovery, then you might understand more about your database design. And then once you start thinking more about database design, you might start needing to know that you need to know more about internals, the internals of how Oracle works, and how that moves on to the features. So you keep on learning and learning and learning. And people think about learning spiraling to the center until you know everything. So you're a Tom Kite or a Jonathan Lewis of this world. But actually, you do spiral out and out and out and out. And you start realizing there's more and more stuff for you to know. So I'm actually a geneticist. This whole computing thing was a mistake. When I went to college, I thought I knew what DNA was and what a gene was. And then I discovered I didn't. For one thing, I didn't fully understand the structure of DNA, and then a gene is made up of various different parts, and now I understand that genes can be turned on and on by control genes. And did you know that actually genes aren't the only thing? Genes can be modified by something called epigenetics, and I'm just learning more and more and more of stuff I don't know. So I'm slowly becoming more and more stupid, which I think is wonderful. There's so much more to learn. So, this is a summary of a diagram. I've been talking about bits of this diagram all the time, and now hopefully all of it makes sense. You know that the buffer cache holds blocks, You know that stuff that goes into the PJ is just for your process, it's not shared. Why the log buffer and the log writer and the log groups are so important. That database is read in by your Oracle server processors and it's read out by database writers. You know that there's all these Oracle processors, but you really don't need to know what all of them do until you have a need to know what they do, or you're just simply curious. But strictly speaking, you can get by without knowing. Everything, all tables, all indexes, and in fact all clusters, which are just groups of them, are stored in the database files in chunks of 8K blocks, unless you've changed that. The only thing I've not mentioned is SQLnet. Now, you remember my analogy about the restaurant, when you go to your waiter, your server processor, or your waitress and ask for your food? Well, SQLnet, the listener of SQLnet, is like the maitre d' at the front of the restaurant, and all that does is say, this is your waitress for the night, and you're sitting at this table, and then you talk directly to your Oracle server process. Okay, I hope that all makes some sort of sense. This is where the presentation ends, but any questions that have come in or any more that you wish to ask, I'm just going to sit here and sip my beer for a little while and answer as many questions as I can.
Okay, so there were many, but well, Kranti asks if you do training sessions.
I used to train people a lot. I love doing training. The problem is that I work for myself and I don't have time to produce nice, shiny training manuals. However, anybody who wants me to do a training course for them, then I'm always happy to discuss that, as long as you understand that I will be giving you printouts, slides that look like they come from the year 2000. But I've taught people to do SQL of Oracle and MySQL, Persuasion, PL SQL, and performance tuning and database design. So I have done a lot of training over the years.
A lot of thank yous. Also, people from Poland and Polish user group, Oracle user group, say hi. Prezemska. He asked about the minty vodka or something. I guess that's.
Oh no. So I do a lot of presentations, and last year I was invited to present at the very first, for a long time, Polish Oracle user group. And the Polish people are very friendly, very warm-hearted, very technically strong, a wonderful group to present to. The only problem is that they're used to drinking more than I am, and most of them are a lot bigger than I am. And to show their appreciation, they get you to drink shots of vodka with you.
Yeah, a lot of people from Poland, from Polish user group, are online apparently. Kamil, Lukas, they all say hi.
Brilliant. So yes.
Again, thank you very much, Martin. And there are many questions, but we can't answer them all. It's been almost 90 minutes. I sincerely apologize for not being able to ask all the questions, but there has been hundreds of them. The most common question, though, is this webinar recorded? Will we get a copy of it? Yes. Mm-hmm. Give me a day or two. I will send every registrant an email which has a link to the recording of the webinar and a link to the slides. So that's the most common question, and I'd like to answer that here once and for all. Martin, again, thank you very much. I truly appreciate you for being here, and hopefully we'll see you soon with your webinar about DRM programming. Was that the title?
Yes, that's another Polish thing.
Okay, I'm thinking about that as a Christmas webinar, maybe like holidays webinar. We should talk about that.
Yes, that could work. It's been a pleasure doing this. I hope people have found it useful, and I'd be happy to do another seminar sometime in the future.
Thank you, guys. Thanks, everyone. And see you in the next webinar. Bye-bye.